Dear, dear students, so in this class we will discuss about load sharing of two transformers which are connected in parallel, that too with the equal voltage ratios. So after seeing the necessity of parallel operation of two transformers and conditions for operation of two transformers in parallel, now let us see what is the load shared by the two transformers with equal voltage ratios. So equal voltage ratio means both the transformers are having same voltage ratio. So here there are, the first condition is parallel operation of two transformers with equal voltage ratios. Equal voltage ratio means here they are given for us with two transformers. So this is the first transformer. So this is the first transformer and this is the second transformer. So first transformer induced EMF is also E. Similarly, second transformer induced EMF is also E. So both these two transformers, they are connected in parallel fashion. They are connected in parallel fashion, and both they are excited from the common supply, that is V1. So primary of both the transformers, they are connected in parallel across the power supply means, that is, so power supply means voltage is V1 in this case. And first transformer, it is having its resistance R1, reactance X1, and its combination is impedance Z1. So resistance R1, resistance X1, impedance Z1, all these are the parameters of transformer 1. Similar, and I1 is the primary current of first transformer. Similarly, second transformer resistance is R2, second transformer reactance is X2, second transformer impedance, that is combination of R2 and X2, that is impedance Z2, it is the parameters of another transformer which is connected in parallel with the first transformer. So current I1 is the load shared by first transformer, current I2 is the load shared by the second transformer. So both these transformers, they are connected to the common load here. Both these two transformers, they are commonly supplying to this same common load. So I1 is the current shared by the first load, I1 is the current or load shared by the first transformer, I2 is the load shared by the second transformer. So at this point, if you apply KCL at this point, then total current I, which is supplying to this load, common load, I is nothing but at this point KCL I1 plus I2, that is the mean, and the supply voltage, voltage available across the load is V2. Whereas with voltage ratios, the condition is what? Here two transformers, they are operated in parallel. So this is first transformer and this is second transformer. Both they are connected in parallel, and they are having its own resistance, reactance, impedance, and load shared by the first transformer is I1, load shared by the second transformer is I2. Both these transformers, they are supplying to the common load here, and total load current I is equal to I1 plus I2, whereas its terminal voltage is V2. Okay, so they are having same equal voltage ratio E and E. Okay, now first case is load sharing in case of similar and dissimilar transformer. So here first we will discuss for similar transformer, load sharing in case of similar transformer. Similar transformer means equal voltage ratios. Equal voltage ratios means here also first transformer E, induced EMF E, second transformer induced EMF is also E. Both are having same induced EMF. If it is having same induced EMF, then it is called as similar transformer or equal voltage ratios. Okay. So when two transformers are having same equal voltage ratios, then what is the load shared by first transformer, that is I1, and what is the load shared by second transformer, that is I2? This we have to calculate it. Okay. Now let us check the description here. Let us now consider the case of two transformers connected in parallel having equal voltage ratios. So as I told you, there are two transformers which are connected in parallel and both are having equal voltage ratio E and E. Okay, the two transformers having no load secondary voltage same, because here if it is load, even though here there is some load symbol we have taken, but it is as good as no load. So here the two transformers having no load secondary voltage same, because here if it is no load means it will be having same induced EMF, that is First transformer induced EMF, if I call it as E1, second transformer induced EMF, I can call it as E2. Then if it is no load means, then both are having same voltages, that is E1 is equal to E2, that is equal to E. Because of that, here we have taken notation for E1 as E, E2 as E. Both are having same voltages. These voltages are in phase with each other. So both these voltages are in phase with each other. This is possible if the magnetizing currents of both the transformers are not much different. So magnetizing current of first transformer and magnetizing current of second transformer, if they are both same, then voltage induced of first transformer will be same as that of voltage induced of transformer E2. So both transformer magnetizing currents must be same. Okay. This is possible if the magnetizing currents of the two transformers are not much different. Now, with this case, the primaries and secondaries of the two transformers can be connected in parallel and no current will circulate under no load condition. So, in this condition, if the magnetizing currents of both the transformers are same, then no load current, then with this, the primaries and secondaries of the two transformers are connected in parallel and no current will circulate under no load condition. When it is under no load condition, then no current will flow. That is the meaning. And here the condition is both the transformers magnetizing currents are same. With that condition, induced EMFs will be same. E1 will be equal to E2, that is equal to E, and no current will flow under no load condition. And this is the circuit diagram for parallel operation of two transformers with equal voltage ratio. Equal voltage ratio means E1 equal to E2, that is equal to E and E. This is first transformer and this is second transformer, both connected in parallel. So load shared by first transformer is I1, load shared by second transformer is I2, and both these transformers are sharing the load, common load. This is the common load. Okay. Now, if we neglect magnetizing components, the two transformers are represented as shown in figure 2. So, if we neglect the magnetizing branch here, if we neglect the magnetizing branch, then the same circuit diagram can be rewritten once again in the form of this one. This form, because here first transformer induced EMF is E1 or induced EMF is E2. So E1 equal to E2 is equal to E. So this whole thing can be written in the single voltage form. So that single voltage form circuit diagram you can see it. So E1 equal to E2 is equal to E, whereas this part I1 load shared by first transformer, R1 S1 Z1 of first transformer, I2 load shared by second transformer, R2 H2 Z2 of second transformers. Anyhow, they are connected in parallel and both are having same voltages. So the same circuit diagram can be written in this way. So E1 equal to E is equal to E1 equal to E2, load shared by first transformer, load shared by second transformer. So this common load, it is connected for both these transformers. Both these transformers are supplying the same common load, which are connected in parallel. So this is first transformer, this is second transformer, which are connected in parallel. So I1, R1 and X1 are the resistance and reactance of first transformer, R2 and X2 are the resistance and reactance of the second transformer, which are connected in parallel. Then you have to draw this circuit diagram. So I is the total load current. I is equal to I1 plus I2, because at this point here it will be I1, from this point here it will be I2. So if you apply KCL, then I is equal to I1 plus I2. The phasor diagram under this condition is shown in the figure dot 3. In the next slide, we will see phasor diagram. Okay. The two impedances Z1 and Z2. So Z1 is the impedance of first transformer, Z2 is the impedance of second transformer, which are connected in parallel. So both these impedances are in parallel. The values of Z1 and Z2 with respect to secondary are with the values of Z1 and Z2 are with respect to secondary. So the value of Z1 and Z2 here are with respect to secondary means we are at the load side, that is the meaning. Now, since Z1 and Z2 are in parallel, therefore the equivalent impedance is given high. So if these two impedances are in parallel, Then what is the Z equivalent? Z equivalent is equal to product of two impedances, that is Z1 into Z2, divided by sum of two impedances, that is Z1 plus Z2. Okay. So Z equivalent is equal to Z1 into Z2 divided by Z1 plus Z2, or otherwise 1 upon Z equivalent is equal to 1 upon Z1 plus 1 upon Z2. Okay. Then finally we will be getting equivalent impedance of both the transformers. Z equivalent, equivalent impedance Z equivalent is equal to Z1 Z2 upon Z1 plus Z2. Okay. Now, as seen from the phasor diagram, so the phasor diagram here is V2. First, we have to take reference as V2. What is this V2? V2 is nothing but the load terminal voltage, voltage available across the load. Okay. So V2 is equal to I1 R1 plus I1 X1. Okay. So here you can see that source voltage is how much here? Source voltage is of both the transformers are equal. That is E1 is equal to E2 is equal to E. Yes or no? So E1 is equal to E2 is equal to E. So at this point here we are having one transformer, and at this point we are having another transformer. So both they are connected in parallel. And once again here this is the load terminal voltage. So load terminal voltage we have to take it as reference to our phasor diagram. So V2 we are taking reference. So from the tip of the V2 first we will indicate. So to get this V2, first we will take drop I1 R1, I1 X1. The combination of I1 R1, I1 X1 is I1 Z1. So from the tip of V2, first we will indicate resistive drop, then reactive drop. Okay. So take V2 reference, then